love to see AI be able to push our understanding of the universe further. After Mosaic, all of a sudden the narrative shifted. It's like, wait. I can actually, build, deploy, wield these methods in my own organization. That no one did that before. Once something has been trained with some data, you cannot ever remove that data. You can minimize it, you can modify it, you can do lots of things, but you can never remove it.
Why did it make sense for Databricks and MosaicML to join forces?
When we all sat down, the founders of Mosaic and Databricks, it kind of felt like we knew each other. There was so much familiarity. And so it was like, all right, we can make it work.
Welcome to Building with AI, the show where we engage in conversations with world-class AI product builders and leaders. We help uncover tactical insights to help you build and scale better AI products. I'm your host, Haroon Choudery, and today I'm very excited to be hosting Naveen Rao, VP of GenAI at Databricks. Naveen is a serial entrepreneur who has established the first AI chip company, which he later sold to Intel in 2016. He then founded MosaicML in 2020, which was acquired by Databricks for $1.3 billion last year. During this episode, Naveen shares MosaicML's jobs to be done, why MosaicML teamed up with Databricks, the economics of training AI models, advice for teams building with AI, and much more. But before we dig in, here's a quick word from our sponsor.
Autoblocks is the leading AI evaluation platform for product teams. It enables your team to collaboratively iterate on prompts, model parameters, and RAG parameters, while letting you retain full control over whatever frameworks or tech stack you want to build with. Seamlessly run tests to evaluate the impact of product changes on quality. Learn how to ship more reliable LLM products at autoblocks.ai. Now, back to the episode.
Naveen, welcome to the show.
Thanks for having me. Excited to be here.
Likewise, we're very excited to host you. So for folks who might not be familiar with you or Mosaic or Databricks, can you walk us through your background and your journey in AI until today, where you're now the VP of Generative AI at Databricks?
Yeah, I had I would say a little more circuitous route than a lot of folks who are getting started today. I've been broadly interested in the topic of figuring out how to make computers intelligent for a long time. I'll date myself a little bit, but I graduated undergrad in 97. And actually, even back then, I did some research on neuromorphic circuits. These are things that Carver Mead and a few others had come up with. Basically, electrical circuits, transistors, resistors, all of that can recapitulate the behavior of neurons. And it was fascinating to me. That's the time that I learned that, our brain runs on 20 watts of energy. Everything we are is only 20 watts of energy. And clearly, we're not quite there even yet. And back then, very far away from it. And I got very interested in this topic of biomimicry and how that applies to artificial intelligence. And after I graduated, came out to Silicon Valley, did the whole startup thing. It was the dot-com bubble and bust and all that good stuff. And after 10 years in industry, I'd built a couple of chips. I had, built products, video streaming space and DSP, a whole bunch of different areas. So I designed chips from the ground up. I knew how computers work. We still hadn't solved much of this. And so I said, this is kind of the time to either go back and pursue this passion or not. And so I actually quit my job and went back to get a PhD in computational neuroscience. So I viewed neuroscience not necessarily as just a pure intellectual pursuit, but more of like can I take inspiration from this as an engineer? Can I look at what we understand about the brain and actually harvest concepts to potentially make computers better? And, my timing was pretty good. Of course, you don't know that at the time. Everyone thinks you're a nutcase by quitting a very good job and career and then going and getting a PhD. But I think I came out in 2011 and really did have a lot of ideas on how computers are going to shift. And that's right around the time that deep learning started becoming relevant again. I had deep neural networks and backprop started solving problems that we couldn't solve other ways. And so I did some research on, again, neuromorphic circuits at Qualcomm, then quit there and started a company called Nirvana Systems, which was the first AI chip company. That was, we probably sold too early, but sold the company in 2016 to Intel. I started a new Intel AI division and scaled it up and ran that for 3 years. And in 2020, I quit that and started contemplating what the next thing was. And that was when we embarked upon Mosaic.
So you've seen a lot of trends come and go in the ML space. Being in the space for so long, I'm curious, like, what has that journey looked like from Nirvana Systems to Mosaic, and especially in between those two periods that got you really excited about starting another company again?
For me, it's really been the same journey. It's about, can we make machines that can learn from data, that can become intelligent, and actually allow humans to do more, to make better decisions, to be able to, analyze greater amounts of data, find inferences in greater amounts of data. This is, sort of like geek hat on. I'd love to see AI be able to push our understanding of the universe further. That's really been the way I've looked at it, is that science is a game of understanding data. And a lot of times we're limited by our tools. AI is another tool that allows us to make inferences across even more data, more observations. So really that was kind of part of it. But along the way, you have to build products that people use. None of this happens by just demonstrating something in an academic context. You have to build products. You have to make infrastructure and chips and all of that stuff work at scale in order to bring these costs down and make things ubiquitous. To really truly democratize, you need scale. And so I've always understood that, and building amazing products that actually do scale has always been my passion for that reason.
How does the cost and efficiency piece play into the innovation and the ability for folks to be able to get to that place where they're able to solve the mysteries of the universe with artificial intelligence, or really just maximize the utility of these technologies? Where does cost and efficiency sort of play into the grander picture there?
Yeah, it's not a direct link, but I look at it as just more shots on goal. The more people that can be using a technology, the more creative, interesting things happen. We saw a very similar thing happen with the PC. When the PC got to a point where, it was $1,000 or $2,000, you just had this massive effect where so many more people were applying creativity to it. And I think we're going to see something here. I'm a big believer in having more people have access to technology. We'll push that technology forward. And cost has been a big one. I mean, I know there's been this narrative out there, oh my God, it's so dangerous. Only a handful of companies should have access to this. That to me is very self-serving and actually a limiter of the technology. If only a few people have access to something, it will never become impactful. Many people have to have access to these technologies in order to truly unleash that kind of creativity. And so cost becomes a big barrier. When something costs 10, 20, 100 million or $1 billion to even get started, there's only a handful of entities who can actually go after it. But when you start bringing things down into the $100,000, $10,000, $1,000 range, and it's like an exponential increase. It's not a linear thing. Going from 10,000 to 1,000 is not 10 times more people. That's thousands of times more people. So I think there's just this huge lever that you see from bringing costs down linearly to the number of people who can access it exponentially.
Could you describe the difference, I guess, in this latest wave of AI as we see it? So we've gone from, over the past decade, things like multi-layer perceptrons and convolutional neural networks, and over to transformer models and LLMs. And so, having been in the space for so long, is this a fundamentally different type of AI? And also, I'm curious, since you talked about the importance of having a lot of people take shots on goal, is there just a larger pool of folks who are going to be involved in shaping this next wave of AI as well, as compared to the previous waves?
I mean, I think the answer is yes to that. I'll answer your second question first. I've been seeing this for the last 10 years where undergraduate education has shifted. You saw it at places like Stanford and MIT first, where people started learning about things that were advanced graduate topics now in undergrad. And I think it's very standard now. Any CS curriculum includes machine learning now, I'm pretty sure. I don't know of any school that doesn't talk about machine learning. That's a distinct shift. There was no machine learning in undergrad 10 years ago. So yes, the number of people building has just increased. The supply of talent has just increased. Now, what's different? It's funny because you mentioned multi-layer perceptron and LLM as if they're different things. They're kind of the same thing. Really, an LLM or, large language model is basically mostly LLM, and it has this other mechanism on the side of it. It's like more things change, the more they stay the same. What we've really been able to do is enable scale of data, scale of compute, size of the neural network could really truly increase. That was one aspect of it. The other aspect of it is the ability to generate outputs, not just filter them. So neural networks 4 or 5 years ago were really focused on feature discovery and being able to run the data through and create filters of that data. So break down the hierarchy of the data. These LLMs and generative algorithms do that, but they also allow you to run it backwards and say, start with a high level description and actually then go back and fill in the details. This concept has been around for a long time, but really being able to do that reliably has been a big innovation. I would say scale, data, and just the idea of what we call auto regression has been probably the biggest drivers of this kind of a thing. Auto regression, very simply, is that I have a large corpus of text. It's auto labeled because I always have sequences of text that are meaningful. So I can always predict the next word. That's auto regression. So you don't need to go and label a whole bunch of data. It's already kind of self-labeled.
So you started MosaicML in 2021. What were some of the problems that you were looking to solve when you started that company? And also, if you're able to paint a picture for companies before MosaicML and after MosaicML, in terms of your customers, like what was the before and after and the jobs to be done that you were solving for?
Yeah, I mean, the biggest single thing was access to these large model capabilities. So at that time, I mean, in the industry, we all knew about large language models. This is not like some new thing that came out of left field. The transformer architecture was published in 2017 or 2018. And so this is not a new thing. It was not a new thing for us. We knew it was going to be important. We also knew it was difficult to do because scaling up to hundreds or thousands of GPUs was just difficult. Not only that, it's expensive. And so was there a way for us to use compute more effectively, thereby driving the cost down, driving the time down, and then wrapping that together into a set of tools that made it very easy to use? You don't need to understand every, bit and piece of the infrastructure in order to wield it. And so before Mosaic, really, I'd almost say like large language model stuff was very, very niche. There were just a couple places doing it. Google, OpenAI, and Microsoft, there were some efforts, but not at the same scale. So really, it was kind of niche. It's almost backwater in a sense because it didn't have a real purpose yet. But that's true for many technologies under development, is that you don't really know how you're going to use it. And I would even argue today, we're still learning that. Being able to chat with something, okay, that's great, but it's not super useful. There are some use cases that are emerging now that are very high impact, but it wasn't really clear what those things were. And I would say after Mosaic, all of a sudden the narrative shifted. It's like, wait, I can actually, build, deploy, wield these methods in my own organization. That no one did that before. And I think, of course, ChatGPT kind of raised a huge amount of awareness around what a large language model can do, a chat model can do. And so that really solidified this view of like, oh, I can potentially take my data and now interact with it in these natural ways. So then that paved the way for people wanting to control and do this stuff themselves.
And just to kind of close the loop on your career journey thus far, you joined the Databricks team last year, and MosaicML was acquired by Databricks. You're now the VP of Generative AI there. Why did it make sense for Databricks and MosaicML to join forces? What were some of the synergies and mutual benefits that were going to be realized as a result of that acquisition?
Yeah, I mean, there's a few reasons. I'll talk about why it made sense from a strategic standpoint, and then also why it made sense for us to do it. They're not 100% the same. So from a strategic standpoint, large models, diffusion models, whatever, they're all a function of their data. It's the old adage, garbage in, garbage out still applies. So if you have bad data that's inconsistent, you will get, bad models out of it. So the model exists because of data. You can almost think of it as a way of transforming data, making it into a model. So being part of a data platform actually creates a much more holistic approach to the whole thing. So companies have trusted Databricks with their data. They do all kinds of transformations with their data already. That's what we call the lake house pattern. And generative AI is yet another one of these. Of course, it's more impactful, potentially allows you to monetize your data in new ways, but it does start with the data. And so as Mosaic, we solve the piece of once you have the data, being able to train and deploy your model. We didn't have the data piece of it. So in order to create a much larger entity, joining forces made a lot of sense, both for Mosaic and for Databricks. So we brought in the capabilities of large model training and inference. Some of it was already here, of course, but we had a product around it. And then, of course, we are now integrating tightly with the data platform itself. So you have this end-to-end thing where you can ingest data, transform it, and then actually get to an end model that leverages that data. So that was the kind of business strategic part of it. Also, our buyers were very similar. Who was buying Mosaic was also very similar to who was buying Databricks. We believe that we could leverage the sales machine that had been built to now sell a more holistic. And so that's been a lot of the journey so far. On a personal level, and why we thought this would work was there was a pretty tight cultural match between Mosaic and Databricks. And I think most first-time founders have no idea what that even means. It's not anyone's fault. It's just I had to learn that the hard way. When I sold my company to Intel, there was a huge impedance mismatch in the culture. And it's nobody's fault again. It's just that company has been operating at a scale that's not zero for a very long time. So the people there don't really know how to operate at zero. When you're building a new business, you got to go from 0 to 1, 1 to 10, 10 to 100. Like each one of those steps is like, it takes a different sort of culture and mindset. And Databricks has been through that 0 to whatever size you want to call them now, 2.5 billion revenue kind of thing. So I think the founders here obviously have founded the company, understand how to grow from 0 and build new businesses. All the founders, except one, I think, have a PhD. They're all from the academic side of things. That was true for Mosaic as well. These are hard problems to solve, and typically you have to kind of cut your teeth in an academic environment to understand how to solve them. And so I think these alignments made sense. So like when we all sat down, the founders of Mosaic and Databricks, it kind of felt like we knew each other. There was so much familiarity. And so it was like, all right, I think we can make it work. Even if all the strategic stuff was great, but like culturally we weren't aligned, it won't work. I felt like it could work. I think Ali and the other founders felt like it could work. And then we decided to move forward. We moved forward very fast.
Love it. Yeah, it was very exciting when we saw the news several months ago. And one of the questions that I hear most often, and I think folks are quite curious about, is you have this new technology in LLMs, and a lot of companies are trying to figure out what are different use cases, ways of applying that technology to helping them maximize whatever business goals that they want to maximize or achieve. And there's a lot of ambiguity, even still, around how to best leverage that technology. And is prompt engineering the way to go? Is it fine-tuning a closed source model or open source model? Or is it training your own model from scratch? And from what I understand, Mosaic helps with the last two things quite well, with fine-tuning existing models and then also training models from scratch. Can you describe some of the trade-offs between those different approaches? Maybe there's other options at a high level as well. The benefits of each approach and what types of companies or use cases might warrant each of those different approaches as well?
Yeah. So to be clear, we actually do prompt stuff as well. So we are working with the DSPy library to come up with ways to automate prompting. Part of the Databricks platform, we actually have a whole infrastructure around saving prompts and things like this. So all of these are just different tools and tool belt here. Prompting it's easy. It's something you can get going with quickly, and you can prove potentially that there is a use for the thing you're building. So taking a big off-the-shelf model for a POC, doing some prompting is just a quick and dirty way to get something working. And I think you can prove the whole flow end to end. The fine-tuning is actually a wide variety of techniques. It's not one thing. So supervised fine-tuning is you have a bunch of labeled samples, input-output pairs potentially that you want to use. RLHF is more involved. You're actually producing outputs, having humans label them, feeding that back, and doing this kind of over and over again. That's like in the loop. Then there's continued pre-training, which we typically find useful for domain adaptation. So these are, again, 3 broad categories. Then you have things like QORA, these low rank methods, which change only small parts of the neural network. Typically, you use that when you have a serving infrastructure that you want to build small customizations per user. So again, all of these have a place, and they all do different things. So that's the fine-tuning bucket. Then the pre-training bucket, you can think of as continued pre-training, what I just mentioned about adaptation, starting from a random checkpoint. But we actually don't think of it as that different anymore. They're really the same thing, just the initialization point's different. Pre-training from scratch, I'll talk about that one, then I'll walk my way back. Pre-training from scratch is useful when you want full control of the data. You know every data point that went in, you know where it came from. So I think that's key. When we provide a open source model from us or from Llama 3 or Mistral, whomever, you're relying on that entity to have done the work of properly permissioning the data and all of that. So if you want absolute certainty, you need to build it yourself. And we provide that capability. Some regulated industries really do love this. Potentially, you can also modify the behavior in very profound ways because you won't have certain kinds of data in there. You can fully control it. Once something has been trained with some data, you cannot ever remove that data or its effect on the model. You can minimize it, you can modify it, you can do lots of things, but you can never remove it. So that's pre-training. All the various versions of fine-tuning, like I mentioned, continued pre-training is, let's say I have a general model and I have some really domain-specific data that has some jargon in it or whatever, then if I have enough of that data, a few million tokens, now I can start to make the model become an expert. Oh, sorry, one more thing with pre-training is I can actually make the model smaller. I can make a very tiny model that understands that domain really well and is very fast and cheap. This is actually one of our customers, Replit. They did exactly this. They don't need something that can chat about random topics in history. They wanted this to be a really good coding tool. And they had great data for that. So they built a smaller model to do that. That's really fast. And then with continued pre-training, domain adaptation, all of that happens, but you're at the mercy of the model size that was chosen up front. So you have to use, Llama 8B or DBRX, which is 132 billion parameters. So there's some trade-offs there. And a lot of those trade-offs come down to what scale of deployment you're at. As you move up the scale, you want to optimize more. You want to put in more time to make things work specifically for the things you care about and not care about the things you don't care about. And that translates into speed and cost. When you drop the model size by a factor of 2, you get, 1/4 the compute or something like that. So I think these are the kinds of trade-offs you need to be thinking about. So if you start off with a GPT-4 with prompting, and then you say, okay, I proved it out on my POC, and now I want to scale to 10 million users, you're going to be in for a little bit of a surprise when you look at the bill. It likely won't make any sense from a gross margin standpoint. That's what we find over and over again. These things, those solutions just don't scale to many users. That's not always true. It can be true in scenarios where the number of users is high, the customization is high, like prompting just doesn't give you that anymore. It's a great way to get started. And so now what we're providing is basically the bevy of tools to allow you to bake in the trade-offs you need to. And that's not up to us. That's up to our customers. We can advise on when we believe that makes sense, depending on how much data they have, how much scale they're going to have on inference. We can start to advise them on a path to take.
Now, if you're training your own model, are you losing out on the ability of a model to maybe generalize outside of the domain that it was that it was trained on? And if that is the case, then are there ways to continually retrain it? Is that cheaper than having to train a new model with new data over time? Curious about how the economics of that work out as you want to expand on the scope of that model that you trained. Maybe we could use the Replit example as a reference point.
Yeah, I mean, I think, okay, so generality, I don't know really how to characterize that. So you can make a smaller model with general data sets and you'll have generality. But if you start off with more domain specificity like Replit did, you can make that model more general by continued pre-training if you want to. I would argue, though, that is outside the scope of what that model was intended to do. So if you want to build a general model, go build a general model. If you want to build a specific model, build a specific model. And I think the other part of this is that these models are not artifacts that live for years. It's not like, hey, I go and design a car and I'm going to keep that car around for 10 years. Models have a time to live that's like 6 months. So it's probably worthwhile to think, oh, now I've shifted the way I'm thinking about how my model's using. Let's build a new model to go do that. There are lots of ways to leverage the training that's gone into a model. Sometimes it's worth it, sometimes it's not. I'll give you an example. If I trained a 1 billion parameter model on 100 billion tokens, that's relatively cheap. That's something that's, I don't know, a couple $1,000, let's call it. I'm just off the top of my head. It's on that order. And let's say that data it's trained on is very specific. Now, if I want to go add general capabilities to it, it's probably not worth trying to push that and modify it into a place where it's more general. And if I'm blowing it up to 5 billion parameters, I basically saved maybe $1,000, maybe. And you added a lot of complexity to the situation. So in that case, I would advise a customer, hey, just start from scratch. It makes a lot more sense. If I have something I needed to have sort of general chat capabilities, but now I really want it to be able to understand tax code really well. That's where I'm like, okay, maybe start with something general, and now let's hone it into a tax LLM. That is worthwhile because the tax code stuff that I'm going to be training it on doesn't have the ability to make it chat in English, right? So I need to have both capabilities. So there are trade-offs here. There are also ways to like what we call upcycle models. If I have a model that's really good, I can potentially make it into an MOE. MOE is a mixture of experts, so I can blow it up into a much bigger model and then continue to train it. So these are all techniques that we do support actually, but we don't yet have a clear opinion on when that works well and when it doesn't work well. The application space is still so big and so undefined that we can't come in and say this is definitively the best way to do it. So right now we're in the space of we provide optionality, we provide some guidance, but our customers might go and try stuff. And it's like, hey, that looks really good. Okay, taught us something,
So you mentioned Replit. I believe Replit trained their own model from scratch, right? Is the type of data that a company has collected, is that indicative of whether it makes sense for them to train a model from scratch or to maybe take a more general model and then make it more specific? Because in the case of Replit, I'm assuming they had a bit of high quality data when it came to question and answering. Was that why it made sense for them to go down that direction?
Correct. Yeah. And they had enough of it. I think the way we've looked at it now when we zoom out is companies have data and they want to have customized capabilities and models. So connecting from that data to the customized model has a whole bunch of different trade-offs. So if you have 100 billion or 200 billion tokens, yeah, pre-training might actually make sense for you. Or starting from a checkpoint of some generality and then adding in your data. There are lots of different techniques like this. We can start with general data and then move to specific data, even within pre-training. We call that curriculum learning. So that actually might make sense for a pre-training flow. If you have 50 million tokens, then you're probably not in the data regime of pre-training. You can do all kinds of things with fine-tuning, continue pre-training. If that data is actually highly labeled, meaning we know this is the kind of behavior I want to see, which we see in call centers all the time. It's like, here's an input query and here's a set of outputs that are good. Great. So now you have a wonderful labeled data set. Let's go do supervised fine-tuning. That makes a lot of sense. And then we can help them on what size model to start from. You don't want to necessarily go with the biggest one if you don't care about all the generality or reasoning capabilities. So yeah, we see this kind of trade-off space happen a lot. It depends on the data size that the customer has. If they have 100 samples, then you're clearly just in this like instruction fine-tuning kind of regime. And maybe you're just in the prompting regime. That could also be true. So things like DSPy actually allow us to do that. So we can think of it as like, here's a set of evaluation criteria that I'm going to establish. Here's data I have. And then here's a whole set of techniques: prompting, tuning, training. How do I best accomplish the goal of hitting a mark on my evaluation that I can leverage all these tools? So I can sweep over prompting, tuning, and training.
That's an excellent framework. I appreciate you putting in those concise terms. And I want to dig into DSPy a little bit. But before that, you mentioned that these models have a shelf life of, I think you mentioned like 6 months. And so between Databricks and Mosaic, we've seen a few models that have been released, from DALL-E to DALL-E 2 to some of the MPT models to most recently DBRX. So a lot of folks that I chat with, they seem to think of these new open source models as almost a moving target. They might have some analysis paralysis because it's, all right, I'm just going to wait for the next one and the next one. And so what is a good way to think about the usefulness of these models, the shelf life as you described before, and how to approach the use of these models, knowing that there's going to be better versions or iterations that come out in the next few months?
We built DBRX and actually even MPT for two major reasons. One was it's a demonstration of what our platform can do. Literally everything that went into DBRX is available to our customers. So you can be at the absolute bleeding edge of models if you choose to be. So we bring customers that capability. So that it's like a reference design kind of strategy. That was one of the major reasons for us to do it. The other one is we demonstrated the use of this mixture of experts architecture, which has some really nice economics. It's roughly 1/3 the amount of compute required to get to a certain performance, which we demonstrated with it. There's no better way to do it than to show it, right? As opposed to talking about it and citing papers. We just did it. And we showed people that, yes, you can actually get to this performance in this dollar amount by using this architecture. And then also the serving performance, the inference performance is better. Another factor of 3 or 4. So those two items were the main kind of demonstration capabilities. And then we said, look, you build this model, it's a great artifact for companies to build off of, and they can leverage those economics that we just talked about. So I think that was really why we did it. Now, why would a customer want to jump on now? You got to jump on at some point. There's going to be a continuous flow of these things. It's one of these things that it's best to understand how the process works rather than waiting for some perfect thing out there that's gonna make your life great. That's not going to happen. You're going to need to customize. You're going to need to build systems. You're going to need to do vector database stuff. You're going to need to do embedding model stuff. All of this is going to be true. If you want to get going, this is what I tell customers all the time, you're going to have to jump in and start to understand how these things work. When I turn this knob, how does that affect performance for my domain? And when you get started, you build something that crosses a threshold of usefulness. Okay, now you have something you can go and put in front of either internal users or customers, and then you're going to learn from that. In the Databricks platform, we actually have a whole harness around that feedback. When people go and use these models, we can log all the responses. We can log feedback. It was a good response, a bad response. If it's a bad response, what's a better response? This allows you to continually improve the model. And that's what we mean by this is a continuous loop. Once you get on train, you can make trade-offs. You can say, you know what, I'm going to need a bigger model to get the reasoning capabilities I need. Okay, go do that. Or, you know what, I didn't need that. I'm just wasting money on every inference. Let's go see if we can make something smaller that hits the same performance. So you learn as you build.
Yeah, wise words. And I think the misperception that a lot of folks have is that once these new models come out, they have to just re-engineer the entire system from scratch. But it's basically marginal improvements from there, right? So I want to go back and revisit DSPy, which is a programmatic framework for optimizing prompts. And I want to get your take on the promise of DSPy, how folks are using it, and then we can dig into the future of prompt engineering. But first, I guess it would be great to get a high-level overview of DSPy and the main use cases for it.
DSPy, it's an open source tool that Matei has lots of responsibilities, one of which is he's a full-time professor at Berkeley in CS. And so this is coming from that side of the house, and we are using it, and amongst other open source tools. And no, I think you hit the nail on the head. It's really about, can you start to put structure around how and why you prompt a certain way? And you do that through creating essentially a feedback loop of evaluation criteria and then trying different prompts out. And that's per model. Prompts are not a universal thing. They're really just a function of the data that went into that model. So just to kind of build a mental model for people out there, the way these transformer models work, our large language model works, is there's representations of different sorts of sequences that it's seen. And so, when you start off with something that talks about a particular domain or is in a certain type of language or a certain style of language, it'll tend to move down that path of that style. So people may have seen like, hey, write a story about a dog, would do it in the voice of a pirate. The reason that works is that it's created a set of dependent embeddings of what pirate talk sounds like. And so you can kind of walk any new sequence down that. And when you prompt something, you're kind of setting the stage for everything that's going to come after it. You're saying, okay, now go into this direction. It's almost like a key into a database, like a soft key into a database. So you're kind of recalling certain parts of the training data that might be relevant. So it turns out that those things that might be relevant is not so simple to do, because part of it is just natural human language. Some of it is that we actually make a lot of assumptions, humans, when we speak. We know, like, hey, I'm on a virtual call with you, and that implies some stuff. It just happens naturally for us. We integrate context very well. And so it's very hard for us to sometimes integrate that visual and physical context into words that actually pull up the right context for the model. And then the model itself, like I said, prompts are not a universal. It depends on what kind of data it's been trained on. So if you have data that overrepresents, I don't know, context about being outside, you probably have to prompt that model differently than a model that overrepresents context from being in a jail cell or something. So so you have a few moving targets here. One is our own ability to understand context, and the other one is what the model does. And you're basically creating the right key. And so the DSPy essentially automates this for a given model once you set a framework of evaluation criteria. This is good evaluation or not. You're basically giving it a hill to climb. And you say, go sample the space and try to climb it.
And so the development process looks a lot less like spell casting, which it looks like for a lot of prompt engineering today. And it looks more like a optimization problem, which I know is very exciting for a lot of folks. How have you seen this sort of play out in experiments with DSPy internally at Databricks? I know I've been hearing about it a lot. I would say the mentions have been increasing over the past few weeks and months. But what are some of the unique advantages or attributes of DSPy that you're particularly excited about?
I think this idea of just making something that's not abracadabra black magic, and putting a framework around it so that you can say, like, I can get some predictability around performance is very important. I mean, look, when we build, or engineers, we don't leave things to guess. I can't say like, all right, I use the right metal, it's thick enough, it's going to be fine. We don't do that, right? We characterize these things and we provide predictability. It's like, no, when I use this material with these, metallurgical properties at this span, I need to make it this thick. And there's like formulas for it. It's very predictable. Much the same way here, going into a customer and saying, yeah, I don't know, why don't you try these prompts and see what works? That's kind of been the state, and it's not a good state. It's a poor state to be in, especially selling technical tools to technical users, that sucks. We don't want to do that. So I think that's the way we're looking at it. Now, it is new, and we haven't really done that a lot yet. A lot of it has been around, here's some prompts that sort of work. We're gonna take those and see if we can make the models perform better. But I think that's what's exciting here, is just putting some predictability around it. Now, we've gotten that sort of predictability now around pre-training, fine-tuning. We can, within a few points of error, actually tell you what the performance will be on known evals. We can say, put this amount of compute in, put that amount of data in, put this model code in, turn the machine a few times, and out comes this thing that we can predict where it'll be. That's very important. And I think as we go on, a lot of what you're going to see over the next year is this predictability. Customers can come in and say, okay, here's my problem. All right, let's start to, characterize aspects of your problem, write them down into an eval, and then start to understand this is how the inputs interact with the outputs. It becomes just a monetary exercise. Okay, well, if you want to make it 10% cheaper to serve, this is what you'll need to do,
At the company that I lead at Autoblocks, one of the things that we like to say is we're selling determinism as a service, because so much of AI development nowadays is dealing with the non-deterministic aspect of LLMs, and we want to take as much of that unpredictability out of it and make it more predictable to experiment. And DSPy is really exciting for that same reason. It creates more determinism in the process. I imagine one of the challenges, though, is that it requires a team to be able to take that understanding of what they're trying to achieve and translate it into a framework with the right set of evaluations, the right understanding of what the optimization function should look like. And so would you say that is the biggest challenge for a framework like DSPy, is just being able to frame the framework in the best possible way to be able to optimize those prompts?
Yeah, I think this is like any other field that's getting going. Data engineering is a relatively new field. There are skills to data engineering. You have to understand how to characterize your problem in a way that makes it so that you can put some predictability and put processes around it, staff it, fund it, all of that. This is no different. I think that's what we start telling customers is, look, you want to start going down the GenAI world, you can't just rely on OpenAI. It's not going to happen. Like, taking a model is one piece of the whole puzzle. There's so much that goes into the end-to-end performance and accuracy that you need to consider. And you need to understand when your system doesn't behave, why it doesn't behave, what mitigations you can take to make it behave. This is a new sort of clay that you need to learn how to mold. Part of that learning is understanding what evals are. If you can really, truly evaluate the performance of your model in a meaningful way, that gives you a huge leg up on anyone. Now you have all these tools. You can say, okay, I can fine tune with this data. I can prompt with that thing. I can do all these manipulations, and I can measure the effects of those manipulations. If you can't, you're shooting in the dark. And honestly, I actually think some of the big model providers want people to be shooting in the dark, because shooting in the dark actually benefits something that's highly general, big, and expensive. That's not how it's going to work. I think the world is going to be a set of engineered systems, and those engineered systems need to have predictability, determinism, and people who understand how to wield those systems at scale.
So aside from DSPy, I'm curious, what are some other emerging techniques or architectures that you're most excited about?
I mean, I think the MOE has been a big shift in terms of the economics. You can get on a single batch, you can get something that behaves like a much larger model for the cost of a much smaller model. So I think that's a pretty significant bump. Obviously, that combined with precision changes that are happening in hardware, we've been able to leverage FC8, floating point 8. I think we're going to keep pushing that down. This just keeps driving costs down. It's really just a no-brainer. When we package it up, make it work. Making these things work, by the way, is not so simple. Like, when you change the precision, it can change the way the neural network actually learns. It can create some instabilities, and you have to engineer those instabilities out. So that's what we do. We provide this definition that we believe is stable. and we can give it to customers. So customers don't have to think through all of that. We do that work for them. These are not really, I wouldn't call architectural changes. They're sort of continual tweaks that make the economics better. What big architectural changes are coming? I mean, I think this idea that models are one part of the whole thing and not the entirety is important. You start looking at deployments, they don't look like they did a year ago. It's like even OpenAI and everybody else, here's our model, just like turn on the wild internet, go for it. It says all kinds of wacky things, right? You can't really do that. And it's actually somewhat akin to even when the internet became a thing. Like everyone, like back in the day, like people would just have their computer connected directly to the wild internet. You could see port scans, anything that just hit your computer. Now we always go behind a router. It's a very standard thing. Like neither of our computers are on the wild internet. They have some sort of network address translation and some other stuff going on. So I think we're seeing that transition happen pretty fast here, where I don't just put an LLM in front of a user directly. I have input filtering. I have prompt engineering. I have vector databases. I have embedding models, all of that stuff before it even hits the LLM. Then the LLM becomes one thing that has a particular purpose. It can integrate context. It can produce good outputs in whatever human language you want or whatever language you want. And then once it's produced that output, actually filtering that, making sure that it's not doing anything bad. It's not saying swear words. It's not putting PII out there. You can do all this kind of filtering post generation, then maybe drive it out to your user. That system is going to get more complicated. So I think that architectural shift is pretty exciting one for us. In terms of the longer arc, I mean, what's becoming very clear is that intelligence and learning is not something that you're just going to keep tweaking up the current paradigm and you're going to have a super intelligent being. It's just not going to happen. All of these things are converging upon what we see humans do because humans have created the data sets and labels. These models reason insofar as they're given examples to allow them to reason around, but they're not really doing novel reasoning because that becomes a search space problem. And so what I think is going to be really interesting over the next 5 or 10 years is going to be how we reduce the size of problems through learned transformations. Then within some sort of problem space, we can actually do this kind of, search for optimal solution. Now we start getting things that could be truly insightful, could be finding new insights that it's never seen before. We're not really there yet. That's not what a model does today.
Incredible. Well, Naveen, I know we're 5 minutes from time, so I'll wrap it up with just a couple of final questions here. One is, what advice you have to founders and product teams who are looking to build with AI?
I think founders, don't go and just try to play the game that everybody else is playing. Find something that's different. Hopefully that thing you find that's different has a large potential. I usually look at these things as like a technology arbitrage. Like find something that is drastically underpriced and that you can create value around and then sell it. That's key. It's not just about, oh, I'm in this space, I need to do what everyone else is doing. I see that mentality a lot, especially right now. Go do something new. Find a way that yours is better. Something about the economics. At the end of the day, technology products are about economics. If you cannot hit certain economics, or if the physics of the world don't support it, you probably don't have a good product strategy. So really think about the economics firsthand. And that's coming from a technologist, the general advice applies when you build teams. Don't compromise. Build the best possible teams out there. The first 10 people you hire will set the stage for your entire product journey for years to come. Do it right. Do it well. And that's going to be a differentiator for you as a company.
And finally, so what excites you most about the potential impact that Databricks is going to have on the enterprise AI space and even more broadly than that?
Yeah, Databricks is really good at interacting with the technical users within a company. And we sort of touched on this throughout our entire talk. It's like, this is creating a new discipline within companies. It's like data engineering plus. Like, how do I make data into something that adds value through generative AI? So call it an ML engineer or generative AI engineer, whatever. but actually enabling those folks, which is an emerging category, to become super productive. To me, that's it. That's the holy grail. Once we do that, we create a ton of value. That value is very sticky and enduring, and it's just going to keep building on itself. And we're going to learn from our customers continuously how to better serve them. So I love getting into that loop of like, wait, we just added, you can do this that much easier. Oh, wow, cool. I'm going to do that. And they go do something new. And then you're like, oh, that's a whole new pattern. So this discovery is very, very fun for me to see. And it's really kind of a continual product journey. We're just at the very tip of it right now, because I know everyone says that, oh, it's just starting, this and that. But the reason it's just starting is that we have to establish this new discipline of how to use these tools to actually get the effect you want.
Naveen, thank you so much.
Absolutely. Thanks for having me.